Okay, this is a re-recording of Chapter 8. We're going to do Chapter 8 by sections, and this is going to be our first section. This is going to be Section 1. And looking, here we go. Section 1 is just advanced. We're going to look at the potential energy of a system. So we're going to talk about a very general definition about potential energy. And really, throughout this course, we talk about conservative and non-conservative forces. And this is really our introduction between what is conservative, what's non-conservative. So we say a force is conservative if it maintains the mechanical energy of the system. Basically, the work done on an object between 2 points is independent of how it gets there. And that's very, very important because we want to be able to assign this idea of a potential energy to different points in space due to this force which is operating on whatever object we're talking about. So the work depends only on where we start and where we end up. And of course, the example that we use throughout this chapter is going to be gravity. Depends on how high you are. I mean, the higher the altitude, the more work that gravity can do on you, and therefore we can assign potential energy to that. So any conservative force that you can have a potential energy function associated with it, will be similar to gravity, where our position determines what our energy is. So conservative forces include gravity, the electric force, the elastic force. The magnetic force is sometimes shown as being a conservative force. The strong and weak forces even get into a more complicated situation that we're not going to talk about. But there's actually a deeper and more rigorous definition for conservative forces. So whether or not the magnetic force falls into that depends on how you do your definition. And it has to do with Stokes' theorem, has to do with vector calculus. So we're going to stay away from that. And again, in this chapter, we're going to stick with gravity as our conservative force. When we get into the next semester, we'll talk about the electric force. And also, since elastic force is a restoring force due to a spring or an elastic material, also conserves mechanical energy. That, of course, can have a potential energy associated with it. So we need a conservative force, otherwise we can't have a potential energy with it. So for instance, friction we'll see as a non-conservative force will never have potential energy associated with a frictional force. But with a conservative force, we know that earlier on we define the acceleration, we define the work done by a force by this general equation right here. F dot dr is equal to the integral starting at point A, ending up at point B. So if we say that this is the work that can be done on an object, if we have a force doing work on an object, okay, that energy has to come from someplace. So for conservative force, if we're doing work on an object due to this conservative force, due to this conservative field, we say, or we do sort of an accounting method here, we say that the change in potential energy, the potential to do work, the change in potential energy is equal to the difference in potential energy of where it ends up compared to where it started out. So again, just depends on where do I begin, where do I end? And that is equal and opposite to the work that the field or force will do on that object going from point A to point B, okay? So it's not as complicated as it sounds. As work is being done, okay, as work is being done, I'm losing potential energy, okay? And if I do work on something to raise something in a conservative field, my potential energy will go up. So just a case of this is we use gravity as an example. If you're going uphill, okay, you're putting work in, okay, and that is adding potential energy that's adding gravitational potential energy to you. As you get to the top of the hill, your potential energy is maximum, and then you can go downhill. Instead of you doing work, you can have gravity do work for you. Normally, we ignore the work done by a conservative force. We basically say we're going to look at the change in potential energy and only consider work done by non-conservative forces when we tally up the total energy of a system. So, for instance, in the work energy theorem, we'll say the work done by non-conservative force is equal to our change in potential energy plus our change in kinetic energy. So again, the work done on a particle going from point A to point B is equal and opposite to its change in potential energy due to that force going from point A to point B. It's just conservation, okay? If that potential energy is being used to do work, that energy is no longer potential energy. It's become some other form of energy, maybe mechanical energy. I'm sorry, maybe kinetic energy. So let's use the force of gravity near the surface of the Earth. We're going to use F equals mg as our conservative force. This is an approximation, but it's a good approximation because when our motion is much smaller than the size of the Earth, the gravitational acceleration is not going to change. But if we look at this, we can say, all right, our force is weight, okay? The direction that we move is going to be in the y direction. So, if I have the force that I'm talking about, it's going to be the negative y direction, negative mg down, okay? If I dot that with dr here, dx is going to be perpendicular to the field, so there'll be no component from the dot product there. dz will take to be in another direction horizontal to the surface of the Earth. That dot product will also be 0. So F dot dy, okay, will just become negative mg dy. Mg is downward, okay? The negative signs will cancel each other out. We're going to think that the mass is constant, okay? We're going to say that the acceleration of gravity is constant near the surface. And we're just integrating from A to B. We're integrating dy from A to B. And that just becomes our delta y, our change in height, okay? So we can see here, as I go up the hill, delta y is going from a lower number to a higher number. My potential energy is increasing. Delta U here, our potential energy, is getting larger and larger. As I go downhill, that potential energy, delta y, is going from a larger number to a smaller number. Our delta y is negative. So our change in potential energy is negative. But that energy that I'm losing in potential energy is perhaps making me go faster, or perhaps working against friction or something like that. So that's a very simple example of how we can take this integral. Actually, it's just our work integral. We've thrown a negative sign in front of it, and we can take a force, plug it in there, and get a result for potential energy. So near the surface of the Earth, we can approximate the change in potential energy as being mg delta y, okay? Now, it's important to point out that not only is this an approximation, okay, but we're really only interested in how the energy changes. We're not as interested in terms of the absolute energy, okay? Now, only to the degree that energy changes will I get work. We can start from a very high potential energy and end up in still a very high potential energy, but there's very little energy that's been transferred from potential energy to something like kinetic energy. So it really doesn't matter what I call zero, okay? Zero energy, zero potential energy. As long as I'm consistent in my system and I use the same reference energy, just like, with coordinate systems, as long as I always use the same origin, I'm fine in describing motion. as long as I always use the same reference point, I'm fine for doing that too. So for instance, oftentimes we'll say, well, zero gravitational potential energy is sea level because that's the lowest that we can go. Maybe if I'm on a roller coaster, it's the lowest point of the roller coaster would be zero. It just depends on the system a lot of times. But again, it's important to define a 0 point for your gravitational potential energy. And when we define absolute potential energy, we'll often define it in terms of, referring to, um, a distance where the field goes to zero, infinite distance, and call that our zero potential energy. Okay. And again, once the position's chosen, we're going to keep it that way. So here's a good example. I have a book here. I lift it above the table. Its potential energy, if the table surface is zero, is going to be different than if I'm holding it over the floor at the same level, of course. Okay, which would be different from if I'm holding it out the window if I'm on the third floor, which in fact I am. So again, the potential energy reference point is going to really depend on the problem that you're solving. It could be, a surface on a table. It could be the floor. It could be the ground far below. As long as I always, take a look at my reference point and keep it constant, I'm fine. So I could do a problem where I'm dropping the book on a table. It makes perfect sense that that table surface is my 0 point. I could be dropping it on the floor. How fast is it going to be when it hits the floor? Well, if I make the floor the 0 reference point, that makes it very easy for my calculations. Or if I drop it out the window, on the ground, how far is it going to fall? So again, here's an example. We have a soccer ball. Just like the book, we hold it some distance above the ground. Our potential energy here I've defined in terms of the ground. So my distance y is using a reference point as y, y equals 0 is on the ground. So when it's on the ground, potential energy of the ball would be 0. Makes perfect sense. Gravity can't do anything to it. It's on the ground already. It's not going to gain any kinetic energy once it's on the ground. When it's in the air, the kinetic energy, the maximum kinetic energy it can get is from falling and hitting the ground. Okay. And there are my potential energies, mgh. Oftentimes I'll write the potential energy is mass times acceleration of gravity times height, because we've chosen the height from the ground as our reference point. Again, it's important to note that in these systems, energy can be relative. Let's look at a relative case. Here we have a skier going from point A to point B. We know what's going to happen here, okay? Obviously, at the top of the hill, she has more potential energy. As she goes down, that potential energy is converted into kinetic energy, and she's going to go faster and faster as long as there's no work being done by friction, okay? So highest energy point at the top of the hill, lowest energy point at the bottom of the hill. It doesn't matter where my reference point is. If I set the 0 point to B, then I will have positive potential energy up here and 0 potential energy here. If I set my reference point as A, I will have 0 up here and it'll just become more negative. That's a change in potential energy, which is important here because that's what I'm going to use later on to calculate my kinetic energy. So for instance, again, calling out our reference point, our initial point, as having positive potential energy and the ground, the base of the hill, the base of the hill has 0 potential energy. I would say that my initial potential energy is mass times acceleration of gravity times the height from the base of the hill. That gives me 5.88 times 10 to the 3 joules. Her mass is 60 kilograms. Acceleration is 9.8. The hill is 10 meters tall. So that is my initial potential energy. At the base of the hill, y goes to 0. So I say that my final potential energy is 0. Final minus initial, I'm looking for change in potential energy, final minus initial. becomes negative 5.88 times 10 to the 3 joules. So I know that energy I've lost has gone someplace. Probably most of it's become kinetic energy. What about the case where I've chosen the top of the hill as my reference and the bottom of the hill as negative 10 meters down? That's allowed, okay? Here, my final potential energy is going to be 60 times 9.8 times negative 10, because I'm negative 10 meters down from my reference point, but I still get the same answer. Final minus initial. My initial is now 0, because at A, I've said that's my 0 energy point. But again, the change still becomes the same, regardless of our reference points, okay? The answer is the same no matter what. Now, if we take Newton's universal law of gravity, we will see in some cases it is more convenient to represent zero energy, a distance at which the forces go to zero. Now, for instance, gravity, by Newton's universal law of gravity, F only goes to zero if the distances between masses is infinite, okay? So we can rewrite this integral going from, instead of a starting point to a finishing point, we can say that our energy is defined, so we're doing absolute, not change, is defined at some distance r compared to what it would be if the particle were completely free of any gravitational forces. That would be r equals infinity by this expression here. So I'm just changing my starting and final point. Obviously, I'll never reach a distance of infinity, but I can at least assign an energy associated with that potential energy. Now, this is important. For these systems, when we have attractive forces, that is going to produce a negative absolute potential energy, okay? If our reference is, again, when the force goes to zero. That's because, think about it, if two particles are bound together, I've got to do work. I've got to put energy into the system to overcome that potential energy, to free them. So oftentimes for attractive forces, be it gravity, which is always attractive, or for electrostatic forces where I have a positive and negative charge, that potential is going to be negative. And later on, we'll talk about potential wells, and we've got to climb out of the well to free the particles. So again, U is negative because it just represents how much work, or is the opposite of how much work I need to do to free them. So taking a look at this, I can integrate F dot dr, doing it in the radial direction. So in this particular case, I can take G and the two masses out of the equation. I can just bump them out front. And if I take the product of R dot dr, okay, I'm just, I'm just getting dr out of that. Instead of the vector dr direction, I'm just getting dr out of that. And I'm left with 1 over r squared. The integral of 1 over r squared, we'll just do our power laws, r to the minus 2. If I take the integral of that, that becomes negative 1 over r. And notice I've got my negative sign here. That negative sign goes away. I integrate this. And now our potential energy actually depends on the inverse of the distance, not the inverse of the distance squared. So the energy actually drops off much slower than the force does. And of course, we integrate with our 2 points at infinity and r. Oh my God, what am I going to do with infinity? Well, 1 over infinity is equal to 0. So my final will be 0. I'm going to subtract off my initial, my first point. So it becomes negative G m1 m2 over r. Okay, so we'll use this later on when we talk about absolute potential energy due to a gravitational field. So again, conservative forces, if they're attractive, like we've got two masses or a positive and negative charge, the potential energy associated with that is going to be negative in most conventions, okay? In most conventions, if it's a repulsive force, then that potential energy is going to push the particle away, okay? And that's going to be a positive potential energy, which becomes less and less until finally it approaches zero. So repulsive forces have positive potential energies associated with them, okay? And again, that's just our typical convention, taking the potential energy to be zero where the forces go to zero. What about the elastic potential energy? This is Hooke's law right here. It describes a spring, or it describes some type of elastic system. It says that the restoring force is in the opposite direction of displacement and is proportional to the spring constant times the displacement. So again, we're going to calculate potential energy here. We get F dot dr. I'm going to plug in for force, negative Kx, okay? Kx is in the opposite direction of the displacement. Thus, the negative sign, and the negative sign cancel out. I'm going to take K, I'm going to put it out front, and I simply have the integral of x dx going from 0 to x. I know I should have primed one of them, but you understand. So we look at this. This looks a little bit strange that there's an x just sitting up here. Oh, going from 0 to x, that's what happened right here. Got flipped. Love PowerPoint. But if I take the integral of x dx, I get 1/2 x squared. That's where the 1/2 comes from. And 1/2 kx squared becomes my potential energy, okay? Where x is the amount of displacement. So if the spring is unstretched, there's no potential energy. If I stretch it out and release it, that potential energy is going to be turned into kinetic energy. But we can see this in two different ways. We can see by plugging in Hooke's law into our expression for potential energy. We can also see this if I graph this, right? If I graph force as a function of displacement, the area underneath the graph, which would be, of course, the integral, the area underneath the graph is the area of a triangle. 1/2 the base, 1/2 the base is 1/2 kx. So I'm sorry, times the height. The base is x, the height is 1/2 kx from Hooke's law, and 1/2 the base times the height gives me the same result. So again, examples of conservative forces. We've already defined potential energy for gravity. We're near the surface of the Earth, and we just pick some reference point. U is equal to mgy. If we're talking about gravity in terms of longer distances, where we're approaching distances the size of the Earth or whatever's pulling, then we have to use the U is equal to negative G m1 m2 over r, not r squared, over r. Spring force, U is 1/2 kx squared. Electromagnetic force, the electric force satisfies the terms for a conservative force. But again, when you get into vector calculus and you start talking about conservative fields, you would realize that the magnetic field doesn't fit all the criteria that most people would define as a conservative field. It doesn't, it conserves mechanical energy, but there's some problems with other aspects of it. So again, we can assign a potential energy to any of these conservative forces. Again, potential energy is associated only with position. It doesn't matter how I go from A to B. It's simply where I start, where I end up. Potential energy is a property of the system. And again, not the object. This is important because the system is the object and what's pulling on it, the field. The system, again, is a collection of objects that will interact via forces. Let's do some other examples. Potential energy will, we know that potential energy is basically, in this case, force times distance. So, climbing a mountain, we would have to do so much work to gain potential energy. So, oh, here's a good example. A wrecking ball, great example of potential energy, kinetic energy, and conversion. Remember, a conservative force will conserve mechanical energy. So whatever mechanical energy we have in the system is going to be pretty much continuing on unless we have some non-conservative forces like friction slowing it down. So this wrecking ball here is used to deliver a lot of energy very, very quickly and tear down this building. Now, why can't we just apply a force and use that to knock this over? Well, the problem here is that if this is structurally strong, the strength of the material will oppose any applied force you have here, and you need to deliver a large enough force that it's going to break. I guess is the idea that I'm talking about here. So you need to convert potential energy into kinetic energy. After it's kinetic energy, it's going to collide, and that inelastic collision with the wall will deliver a lot of energy quickly. And again, a lot of energy quickly, we're going to see is associated with a very large force, and this creates the force that we need to overcome the bonds of the material. So again, wrecking ball potential energy is turned into kinetic energy is turned into work, and the work is what's going to tear the building down. Wrecking balls range in mass from about 450 kilograms up to about 5,400 kilograms. And just to give you an idea here, because again, to understand how demolition works, we're not just delivering energy, we're delivering energy very quickly. And this is what's going to deliver a breaking force to the object. So we'll consider a wrecking ball with a mass of 5,000 kilograms. We're going to use a crane to swing it way up, 20 meters, 60 feet up in the air, okay? And then we're going to let it swing down and go into the building. Just like you swing a hammer back, and on contact, you deliver a massive force. So if we calculate the potential energy of this, and again, 20 meters represents how high up in the air we go. MGY, the reference point is going to be the lowest point of the swing where it makes contact with the building. 5,000 kilograms, that's really quite massive. It's 6 tons. At 9.8 meters per second squared times 20 meters is roughly 1 million joules, okay? So that's the same amount of energy as a pound of TNT. And I don't know about you, but I'm fairly certain that when a pound of TNT detonates, I don't want to be anywhere near that. It has a very large amount of destructive force, as the wrecking ball will have. So again, potential energy, we're going to stick mainly to gravitational potential energy. We can understand that in a system where mechanical energy is conserved, that the potential energy is just going to be traded with kinetic energy, okay? Or another form of potential energy, okay? So for instance, if I drop a ball on a spring, it's going to turn gravitational potential energy into kinetic energy. Then the kinetic energy is going to be used to compress the spring to turn into elastic potential energy, and that's going to bounce back up. In this case, the biker has to put work in because they start up the hill with some kinetic energy, but they've got to convert that work into potential energy. At the top of the hill, they're out of breath. They then start gliding down. Now all that potential energy can be returned to become kinetic energy. Anytime you watch a winter sport, it's a great example of turning gravitational potential energy into kinetic energy and work against friction. So for instance, this is a ski jump, and this is the ski jump from the 2018 Winter Olympics. Gosh, I'm so bad about remembering where all of these took place. But in any case, potential energy is going to be converted into kinetic energy, and then they're going to sail after this pretty much like a projectile. So the way that it works is the ski jump provides you with the mechanical energy. So potential energy is turned into mechanical energy in the form of kinetic energy. And then that kinetic energy launches you off the end, and you follow this landing slope. And obviously, the longer the distance that you travel, the the better your score is going to be. Yeah, there's some aerodynamic effects from the skis too, but for the most part, you're maximizing conversion to kinetic energy to give you that longest range. Now, for Olympic size, to my knowledge, they come in either 90 meters up or 120 meters up. So if you calculate the amount of potential energy at the top of the ski jump, you can get quite a large number here. 80 kilogram person, 120 meters up, is going to have a potential energy of 94,000 joules. And just to give you a reference point, that's almost 400 feet up. That's quite a distance. But in any case, the potential energy is turned into kinetic energy. Same thing is with the bobsled and the luge. Although on television it looks like they're on a level track, they're actually starting these tracks at the top of the hill and they serpentine their way down. The idea here is to convert that potential energy into kinetic energy. And two things happen here. Obviously, the faster you go, the shorter your time is going to be. As you take a line lower on these turns, okay, you're going to convert more potential energy into kinetic energy, but you're also going to shorten your distance through the turn. And again, here's a bobsled. During the 2010 Olympics in Whistler in British Columbia, Canada, you had a 1.45 kilometer track that had a vertical drop of 152 meters, just to get an idea of how these tracks work. So if I were to calculate the potential energy of this bobsled, it would be based on that height difference. We're going from a higher height to a lower height. So here, delta Y is going to be 152 meters. So I would say the bottom of the bobsled run would represent 0 potential energy. The top would represent the mass of the bobsledders at the maximum weight the bobsledder can have with a 4-person crew, translates to a mass, weight mass, of 630 kilograms. So this is really maximum mass. If I multiply that by the acceleration of gravity, by the vertical height from top to bottom, I get about almost a megajoule, okay? Almost the equivalent of a pound of TNT blowing up in terms of the energy that they have at the top. So this shows you why these sports are so incredibly dangerous. If there's an accident and you suddenly release those energies, these bobsled riders are not that well protected. There have been fatalities in both the bobsled and the luge due to the incredible amounts of potential energy. Again, all the downhill sports are the same. It is really, converting your potential energy into kinetic energy while minimizing the work that you lose due to, friction, or in this case, as they cut into the snow, they're actually doing work on the snow, causing it to spray out. Okay. Climbing Mount Everest. Let's say we have the unrealistic situation where you are at the base. No, not the base of Mount Everest. That's the next calculation. You're at sea level and you're climbing to Mount Everest. That would be quite a hike. What is my difference in potential energy from sea level to the top of Mount Everest? Again, I would say my reference point, y equals 0 sea level here. Mount Everest is 8,848 meters tall. I take my mass, multiply that by the acceleration of gravity. That comes out to 6 million joules. That means that going from sea level to the top of Mount Everest, you would have to gain that much potential energy. In more realistically, however, base camp to the peak is much less than that. Base camp to the peak is about 3,500 meters. This is from the base camp from approaching from Nepal. And if you're to do so, you start at an initial height of 5,354 meters, where there's more oxygen. And then you subsequently climb to different camps and summit at 8,848 meters. So the difference there in height is again about 3,500 meters. During the climb, a typical person would have to produce almost 2 million joules of energy to get to the top. Now, the problem is, where's this energy coming from? This energy is coming from work from the muscles, okay? And the muscles are basically converting chemical energy from the body. So as you go higher and higher, metabolism doesn't just work from burning calories, so to speak. It is the oxidation of these hydrocarbons that we are consuming, and some fats and some proteins. But it's the oxidation of this that provides us with the energy. Now, the reason why Mount Everest is so difficult to climb isn't so much that it's a long way up. It's that you are so high, there's less oxygen. If you have less oxygen, your muscles can produce less work. With less work, the climb becomes more difficult. In fact, most of the energy of your body, because there's so little oxygen up there, most of the energy of your body is just trying to keep you alive. More mundane tasks. How about going up a stairs? If you climb a 6-story building, which is 18 meters, that would require a change in potential energy of 12,000 joules. Now, again, climbing stairs, supposed to be good exercise. I try to do it as much as possible because I like to eat. I want to take in more calories than I necessarily need to for my body. So in order to make up for that, we need to exercise. And one way to do this is to use our muscles to work against gravity, to convert the work from our muscles into potential energy. That allows us to get rid of some of the excess energy that we take in by eating that extra helping at mealtime. So looking at a person who's 70 kilograms, yeah, I wish, 9.8 meters per second squared times the change in height climbing the stairs would be 18 meters times the weight, which is 12,000 joules. It doesn't sound like a lot. In fact, a food calorie, we'll calculate later on. We calculated that earlier. We calculated food calorie earlier on, and we found that it's about, 1 calorie is 4.186 joules if it's a regular metric calorie, but a food calorie is 1,000 times greater. So this only represents about 3 kilocalories or food calories of energy. Of course, your body's very inefficient, so you burn much more than that when you climb the steps. Probably shouldn't have told you that. Okay, that's it for this section.